Hello, and welcome to the short animated pencast on molecular group theory. Today, we'll be discussing benzene. More specifically, we will discuss the symmetry of the basis set consisting of benzene's individual pz orbitals. Benzene belongs to the D6H point group, which means we can use the D6H point group character table to find out which symmetry operations can be applied to it. Our first task will be to understand and analyze the effect of each symmetry operation on our basis set. We will store this information in the form of a vector, referred to as the reducible representation of our basis set. As is often the case with vectors, and as indicated by its name, the reducible representation can be expressed as a collection, or, for the more mathematically inclined among you, as a linear combination of its linearly independent constituents, commonly called E-reps. Our second and final task in this pencast will be to use the linear orthogonality theorem to find out which E-reps from the character table make up our reducible representation. But first, some rules. When constructing the reducible representation, we apply each symmetry operation to the entire benzene molecule. We then observe what happens to the position and orientation of each pz orbital to determine its contribution. The first case we'll be looking at is the one in which an orbital stays in place with unchanged orientation. That orbital is said to have a trace of 1, which is its contribution to the reducible representation under that transformation. Orbitals that stay in place will be highlighted with a glowing animation. The second case is when a symmetry operation does not change the position, but inverts the orientation of an orbital. In this case, the orbital is attributed a trace of -1 under this operation. Orbitals which stay in place with inverted orientation will also be highlighted with a glowing animation. Finally, for the third case, if an orbital leaves its starting position during a symmetry operation, a trace of 0 is attributed to it, as the orbital is not symmetrical under this symmetry operation. For contrast with the case in which the orbitals do stay in place, those that leave their starting position during an operation will become transparent. With this, we can start analyzing each of the symmetry operations applicable to the D6H point group, storing the trace of each operation in the bottom left corner of the screen for clarity. We start with the identity operation, which is associated with the action of doing no action, in which case all orbitals stay in place with unchanged orientation. Therefore, the trace associated with each orbital is 1, adding up to a total of 6. Next, we have 2 c6 rotations along the z-axis, which is perpendicular to the molecular plane. In this case, all orbitals leave their starting position, giving each one an associated trace of 0, making up for a total of 0. Next, for the c3 rotation, all atoms leave their starting positions, which means we have a net trace of 0. Next, we have a c2 rotation along the z-axis. Just as the last 2 operations, this one also has a trace of 0. Now we have the c2 prime rotations. Each rotation leaves 2 atoms in place, but inverts their orientation, giving each rotation a trace of -2, making up for a total of -6 when all 3 rotations are considered. Now we have the c2 double prime rotation. This rotation happens about carbon-carbon bonds, hence all orbitals leave their starting position, giving this operation a trace of 0. Next, for the inversion operation, all atoms have their orientations inverted. However, they also do leave their starting positions, giving each one a trace of 0. Next, we have an S3 improper rotation. Since this operation involves performing a C3 rotation followed by reflection, and since the C3 rotation takes all of the atoms away from their starting positions, that means this operation has an associated trace of 0. Next, we have an S6 improper rotation, which consists of performing a C6 rotation about the z-axis, followed by a reflection. Since the C6 rotation removes all of its atoms from their starting positions, this operation has an associated trace of 0. Next, we have the horizontal mirror plane of reflection. Since this reflection happens across each carbon atom, none of them leave their starting positions. Furthermore, since the pz orbitals are orthogonal to this mirror of reflection, all of their orientations are inverted, giving this operation a trace of -6. Next, we have 3 reflections about dihedral mirror planes. Since this operation happens about the carbon-carbon bonding axis, just as with the c2 double prime rotations, all carbon atoms leave their starting positions, attributing their respective pz orbitals a value of 0, giving this operation a trace of 0. Finally, we have the reflections across the vertical mirror planes. Since each plane crosses 2 carbon atoms, each keeps 2 of them in place with unchanged orientation. Furthermore, since there is a total of 3 mirror planes of reflection, this operation has a trace of 6. And with this, we have successfully constructed the reducible representation of benzene's pz orbitals. Now it's time to express it in terms of its constituent E-reps. To do this, we count how many times each E-rep appears in the trace. This can be done with the leader orthogonality theorem, that is, by taking the dot product between each E-rep and the trace and dividing the product by the length of both vectors, as can be seen with the A1G E-rep. This operation gives 0, but that's not the case for all E-reps. In any case, the application of the leader orthogonality theorem for all E-reps can be found here. Please pause and check all of them by yourself. With this, we have reached our objective of finding the irreducible representations that fully describe the symmetry of the basis set made up of the pz orbitals of the carbon atoms in the benzene molecule. But we're not done just yet. Though I won't go into the details in this video, I think it's very interesting to note that once the E-reps are known, further processing can be done to find out which linear combinations of atomic orbitals would have the symmetries described by each E-rep. These of course can be plotted to show the possible symmetries hidden in the basis set we started with.